Hello everyone, I welcome you all to Startup Academy, your online gateway to get success in ISS exam. This academy is exclusively for ISS and we have been coming at the end of this topic time series. In the previous lecture, we discussed about the forecasting method and the two methods how can we forecast. One was exponential smoothing and the second one is Box-Jenkins method. So today we'll discuss in detail about Box-Jenkins method. So Box Jenkins methodology or method, whatever you can say. So Box Jenkins method is a method which helps us to uh, find the which helps us to identify, then find the perimeter or estimate the perimeter, and then finally checking or testing of the parameters whether they satisfied our model or not, and finally making a final model in which that model is meant for forecasting, and the forecasted model is dynamic in nature, which means it changes whenever the value of the time period changes, so it keeps on changing and updating itself. So there are four major steps in this Box Jenkins method. So first of all, if we describe this Box Jenkins method, then it is a systematic procedure of identifying first is identifying, second is estimating, and checking. And checking ARIMA models for time series forecasting. So this is our definition of this Box-Jenkins method. It is the systematic procedure of identifying and then estimating and then checking the RIMA models whether they are fit for time series forecasting or not. So moving on further, the first method or the first step is step one, initial identifying, model identification. So this is the most crucial step of all the steps. So first point would be most crucial or important, whatever you can say, or important step for this procedure. Here we have to find the values of P from autoregressive model, D from order of differencing, and Q from moving average model. These three has to be found out. Now third is the model should be stationary. This is very important. The model should be stationary. Now stationary means constant variance, constant mean, and constant autocovariance function. which means it does not change with time t. So if the model should be stationary, and if it is not stationary, then we have to convert it into stationary. Now, how can we convert a model from non-stationary to stationary? By differencing methods, like we'll do first order differencing, and if there is trend present, and if there is trend and seasonality both are present, then we'll do second order differencing. So that is how we convert our non-stationary model to stationary model. And then from this order of differencing, we'll get the value of d. And for our values of q and p, the third point is the values of q and p are obtained by ARIMA model. So how is it obtained? For ARP P process, for moving average Q process, and for ARMA P comma Q process. So here PACF, partial autocovariance function, cuts off after lag P, and ACF, autocorrelation function, tails off. Here autocorrelation function cuts off after lag Q, and PACF, partial autocovariance function, tails off. And here both autocovariance function and partial autocovariance function, tails off. And hence we find out three values, which are P, Q, and D. So this was our first process. Now PACF cuts off after lag P means that if we draw lag with PACF and there is some lag here, it is P. So PACF is going like this, and PACF is going like this, and as soon as it strikes lag P, it cuts off, means it comes directly down. And tails off means, cuts off means it comes directly down. The value from here becomes directly here, 0. And tails off means it slowly comes down like this. So that is the difference between cuts off and tail off. So moving forward with the second step, step 2. Step 2 says that parameter estimation. Now we can use the procedure such as MLE, maximum likelihood estimation. This gives more accurate answers, so it is used. Or we can use least square estimation process. This is easy and fast to compute. Both have their merits. This is easy and fast. So any of the methods can be used, maximum likelihood estimation or least square estimation. Now the second step is parameter which is estimated is should be should decrease, or what do we say, that parameter should minimize forecast error. That's how the parameter is useful. If it does not minimize forecast error, then the parameter is not useful for us. So minimized forecast error. It should then parameter should verify all conditions of stationarity and invertibility. So parameter should verify all the conditions of stationarity and invertibility as well. And parameter should be significant. Should be significant. So this was our third step in which we have to estimate the parameter. Now the parameter has been estimated like we did in econometrics. Parameter is first of all we estimate the parameter and then we check whether the parameter is which is estimated is correct or not, or is giving us more benefits than the previous one or not. So now the third one is checking. So step 3 is checking. So for checking, first of all, estimate the residual. Now residual is ET, which is estimated as YT minus YT cap, where YT cap is the estimated parameter. Okay. Now we have estimated the residual, and we know that the good model in good models, this residual acts like white noise. Now we know that white noise has mean zero and constant variance and constant autocovariance function. So the residual should behave like that only. And now we have to find the autocorrelation function of the residual, which must lie within 95% confidence interval. This autocovariance residual function should lie within 95% constant confidence limits or confidence interval, or we can say confidence limit. I'm writing it whole. And we can then use our test, normality test. And hence our parameter is verified. And if it is not verified, then what will you do? Then we can we can increase or decrease the values of P and Q from autoregressive model or moving average model, and then we can go to back to step 1 and redo all the procedure again. So and redo all the procedure again, and then reach till this thing only, checking step, and then we'll again check the new parameter. This is how we do. And if it does not satisfy the test again, then we'll move back to first. So this is how our Box Jenkins method is an iterative method. Iterative means it keeps on repeating until our answer is found. So yeah, that's it. There is this one step normality test, or we can use Jung box test. Any of the test can be used for verification or checking. Now the fourth step would be forecasting. So now that we have estimated estimated the value or checked the parameters of our model, now we'll put all the estimated values in the model, and we'll get a final final model, which is a satisfactory model, or we can say after selecting a satisfactory model. After we select the satisfactory model, we use that model to predict, or instead of predict we can write to forecast future values. And this satisfactory model, or the new model that we have selected, can also be known as the forecasted model. So forecasted model is dynamic in nature. Dynamic is which keeps on changing and updates itself, and it updates itself as new data varies. As and when new data comes, data points comes, so this forecasted model will be changed. Suppose this was our model, yt is equals to phi yt minus p plus theta plus wt plus theta wt minus q. Suppose this was our original model. I will write original, and by estimating the values of p, q, and d, we'll get yt raised to the power d, or we can instead write delta raised to the power d. Now we have found out the values of d. Suppose p is 1, q is also 1, and d is also 1. Suppose these are the values that came out in the second step. First step, that we have determined that the this is stationary, and we have determined the value of p, q, and d. Now the second step is estimation. So step 1 is this. Step 2 is estimation of the parameter. So we have estimated the value of phi cap and the value of theta cap. And the third step is checking. It satisfies the tests. Jung box test has been satisfied. Now the fourth step would be forecasting. So now our forecasted model would be yt cap equals to phi cap yt minus 1 plus wt plus theta cap wt minus 1. So this would be our forecasted model. And as and when the values of t changes, this forecasting will also be changing. So value of t is 1, then the forecast value would be 10. And the value of t, suppose we are forecasting the value of a population in a city. Suppose in a city there is, or in a village there are 10,000 people right now. We have to forecast the value in 2020, 2030, after 5 years. So we have changed the value of t from here. As we have changed the value of t, the forecasted value comes out that the village would have a population of 15,000, or 15,000 by 2030. And when we have to calculate the value for 2050, which is 2050th year, then we'll change the value of t again, and we'll find that the value of the village population of the village comes out to be 30 or let us say 25,000. So that is how it has changed from 10,000 to 15,000 for in the span of 5 years, and from 10,000 to 25,000 in the span of 25 years. So that is how we are forecasting the values, and that is how it changes as and when the value of t varies. So I hope that this concept has been clear with all of you. If not, then you can ask in the comment section or on our WhatsApp channel, anywhere. Only relevant doubts will be answered, and this completes our syllabus for time series. In the next topic we'll begin in the next lecture, and all the topics I have covered, and most of the questions have been covered with this. Only the question numerical forms has not been covered, that you can do on your own, and if you face any doubts, then you can ask freely from me anytime you want to. So keep on preparing and keep on learning. All the best. Thank you.